Hello and welcome to today's webinar. My name is David Cash. I'm a member of the marketing team here at Mountz. I just want to say thanks for joining us today, and I hope that you find the information that we are about to talk about useful in whatever practice or whatever assembly you might have. As we look at our topic today on reducing our scrap rates through a smart manufacturing or smart process in our assemblies. And so with this, go ahead and you can chat any questions that you might have. At the end of the presentation, we'll have a time where we can review those questions and give you those answers to those particular questions. So again, our topic today that we are dealing with is our reducing manufacturing scrap rates with a smart fastening process. And so let's go ahead and jump right in. So if we look at the ability for us to use advanced manufacturing products and processes, this can really help reduce those scrap rates. And by using new technologies within fastening that help us to be more precise and provide uniformity within our assemblies, this can really help in that area. And so if we have an automated system that not only can do the assembly but can also monitor what's happening, tell us if there is an error, and help us to remove any error that might happen with that process, that can really help us again in being able to reduce those error rates and in essence the scrap rates as well. And then if we have that ability to collect the data that is happening with our fastening process, this gives us a real advantage, and we'll talk a little bit more about the data collection process here as we move through the presentation. But this gives us, again, the ability to analyze what is happening with our manufacturing process throughout the entire assembly as it relates to our fastening. And so, again, all of that is to say we want to be able to reduce any type of scrap that we have. And this all stems and is encompassed in the ability to error-proof the assembly that we are working with, and giving us the ability to not only detect when a fastening error has happened, but also give us the opportunity to repair that or fix that right at that spot, so the part doesn't move down the line and this error reveals itself later, and again we have either rework or a tremendous amount of scrap that we are dealing with. And so if we have tools that are flexible in nature, meaning that they have the ability to adapt to different types of programs or products that allow us to be able to change the fastening process with having the ability to program different presets to use, different styles of rundowns, the ability to control what happens from when the trigger is pulled on the tool to the final finishing torque and or angle after that. So these types of tools give us a great ability to integrate them into the actual fastening process, into the line control. And again, they just give us the ability to be flexible with how these tools are used in different locations with different requirements for different assembly processes. And again, we can automate a lot of what happens by using an advanced manufacturing type of tool that does give us the flexibility to do the automation process. And again, we can be very, very agile and flexible. If there are changes that need to be made to the assembly, to a specific fastening process or rundown, it makes it very easy to make those changes quite easily and right away. So when we look at the smart assembly process, we want to kind of look at the entire overall from when the part begins until it has been finished. And if we can add the ability to use Industry 4.0 techniques or additional line controls or IOs to do that, we can help to integrate the tooling into that process as well. And so the accountability that we have by being able to monitor all of these different inputs and devices can really help us to see where the issues may be, where we may see bottlenecks, or where we may see actually operators producing at a higher rate than the line can control. A lot of those types of inputs are really helpful in being able to look at that. So we can help to monitor and document what's going on through that entire process. And again, it just gives us more visibility on what's actually happening on the line for our particular setup. And so with the real-time monitoring, we do have the built-in network capabilities with the tooling. So again, we can communicate with either an MES system or the ability to use either Modbus or open protocols to be able to communicate with particular builds if they are more of a high mix, low volume type of scenario where you may have different parts that are coming through the same line. We have that ability to communicate with the tooling and the fastening to automatically adjust for that particular part and run through the different modeling or job assemblies that are available with the smart assembly process. And so that's going to lead us to our poll question today. As we're looking at scrap rates and the error proofing processes, what is your current monthly production scrap rate that you might see? So we have less than 1%, 1 to 2%, 3 to 5, plus 5. So you have those particular items that you can select. And I will go ahead and let our poll music come through here. As I grab a drink of water. All right, we'll go ahead and wrap up the poll question. It looks as we have a tie here for about 3 to 5% and 1 to 2%, with plus 5% coming in the third place there. And so again, when we look at how we can help to control what happens during the fastening process, by the use of using smart electric screwdrivers, we do have that ability to add an error proofing element within the actual assembly process. And so these can be items such as being able to monitor the amount of turn or angle that happens during a rundown. And we'll touch on that here in just a second as we look a little bit more to the error proofing side of the assembly process. But as I mentioned before, the smart electric screwdriver systems allow you to be able to program them to have different assemblies that we can use, different workflows that may also enhance the actual production. And we also then get the actual fastening data that we can use to either look at a specific part that we may be having issues with, see what the outcomes may be from certain fastenings, or it could be the ability to look at the performance of different operators that may be doing the same procedure. And it gives you a way to take a look at what's happening with your actual fastening processes through the data, and we'll touch on that as well. And so when we look at the ability to have multiple fastening tasks with a smart screwdriver, so we can again control what happens from the very beginning of the rundown to the actual end of the rundown, where we have the ability to add different presets together for one particular rundown, or different RPMs, and we'll look at that as well during our scenario example for what we've got lined up for the demo portion of today's presentation. And so with the screwdrivers as well, we do have the ability to add and use the digital IOs that are capable with controlling which preset might be used, which program we want to be able to select. Do we want to be able to communicate with other line control devices such as light trees or part management processes? So we do have the digital I/O aspect with the smart screwdriver as well. And then, so again, as we look at the actual error proofing process, we have several different webinars on error proofing, and you can certainly look back at our previous webinars on error proofing. But for the fastening process, we can not only look for a specific torque value that needs to be achieved, we can also monitor, again, the amount of turn or angle that happens within a fastener. And so we can create an angle or turn amount window. And so if we see common fastening errors like cross-threading or possible stripping or camming out of the actual bit from the fastener, these are all items that we can detect by monitoring the amount of turn or angle that happens within the fastening process. And so when we have our system set up, we can say read the angle, must turn at least say 5,000 degrees of rotation and no more than 5,500 degrees of rotation. And so we can develop a window. So when the torque is achieved, we also have a secondary or error proofing check against the amount of turn that happens with the system, as well as looking at the actual torque and is it within the parameters of percentage that we have requested as well. And so there are other items within the error proofing process that we can use, but that we'll leave for another webinar. And as we look at the actual workflow process that happens with the different abilities for the smart drivers to have multiple presets, this may give you an opportunity to consolidate and combine different operations that may be able to be utilized by using a different preset that may be down the line or reduce the workstations that you have. And by doing this and adding the additional ability to error proof the assemblies, this can help to reduce the scrap rates as well within looking at what actually happens through your fastening workflows. And then, as I mentioned, with the data collection, there is a lot of information that we can look at through not only the fastening process, but if we include additional items such as our PLC or the actual line control movement or different processes within the communication protocols, by selecting and using the data that we can collect, this is going to give us the ability to take a look and see exactly where the process may have some need to be improved, or where we may see too much improvement. And again, if you joined us on some of our webinars on looking at the actual flow of the assembly process. We want to make sure that that process is easy, and that we're eliminating any type of waste through the lean manufacturing. And if you have an operator that may be overproducing, that may be causing, again, bottlenecks and things like that. But you can also look at certain applications and certain problem fasteners, and look at the data that you are seeing with the fastening to see if there is something that may be an issue with some other components, such as the fasteners that are being used. Are there differences from lot to lot that you may be receiving? Have you maybe changed a fastener vendor, and things to that nature? But being able to have the torque event data, this does give more visibility and does give you the actual ability to look and measure and have some ability to create decisions that can be done fairly quickly, and you can move to a place that eliminates some variance within those particular fastenings or applications. The next that really helps with this is by the use of a transducerized tool. And basically what that means is there is a built-in sensor in the tool that is monitoring the actual torque output. So there are different types of smart tools that will be either a current control product where the torque is converted from the amount of current that is being used. There's also, as I just mentioned here, the transducerized tool that does give you that ability to actually get the data output that's happening on the part with the tool itself, having that built-in sensor. And so that's going to bring us to kind of the what we're looking at with different smart control line devices. I mentioned the PLC, which can control a lot of what's happening. You have bit socket trays where the operator must pull the correct bit to be able to use. We can use barcode scanners to, again, add data to that assembly or pull up a certain instruction. There are proximity sensors and pick-to-light sensors that can help guide the operator through the assembly process. And then we can also look at the use of part in and part out management as the part moves down the assembly. Another tool that is being used more and more in the assembly to help reduce scrap rates and alleviate errors is the use of robots and cobots. This doesn't necessarily eliminate the operator, but for very delicate and sensitive assemblies, we can have a cobot used to pull parts, set parts, have the operator go ahead and do the fastenings and the rundowns, or you can use a vision guided system that you're seeing there with the display or the video clip, which allows the cobot to go ahead and perform the fastening. In this case, this particular example is using a ability to be able to change the actual chuck that's being used to accommodate different fasteners for a particular operation. But those types of equipment are being used more and more in the fastening process. So there is one other piece of equipment that could certainly help with this, and we do have other webinars on the use of our DPC Touch position control system. And so what this does, it allows power to only be to the tool when the tool is in the correct location. So we can set up different fastening programs, and the tool is only going to work when it is in the right fastener. So the operator can try and use the tool in any other spot, but there's not going to be any power to the tool unless they're in the correct location. And so by using this particular position system in conjunction with the Smart tool, this gives you the ability to really kind of lock down the assembly and guide the operator through the entire process through visual instructions and feedback. If there is, again, an error, that the operator would need to correct it right away, or they will not be able to move on through the process. And so, again, the DPC Touch really helps with that type of scenario. We're not going to be talking about that in the example, but again, we do have other webinars regarding this particular system to help with reducing the scrap rates. So our particular brand of our DC tool that we use as our smart electric screwdriver, our ECT series DC control tool. Again, these tools are available with a built-in transducer in different configurations, such as a right angle, inline, and pistol grip. But this is the tool that we'll be using in our particular scenario and example. These tools do have the ability to have multiple presets, so we can have up to 15 different presets. We can link presets together with our multi-sequence process, and then we also have some of the error-proofing capabilities that we talked about before, along with monitoring the data and the output that happens from any type of torque or error event that we may see with the assembly. And so if we look at our scenario for what we're going to look at for our demonstration, we have a critical component, and this could be on your end something that is an extremely sensitive piece of the assembly. It could be a really a part that necessarily needs to be secured correctly. If it moves down the line, again, we'll have a lot of rework and things like that. But a critical component that needs to have some finesse maybe assigned to that particular rundown. It's a very fine thread type of application with a long fastener, and it may or may not have a washer stack in it, but I'll talk about that here as we look at the scenario. And so one of the things that that can happen very often with a electric tool with the use of a real fine thread fastener is going to be the ability to cross thread that particular fastener, and that can happen very, very easily if the operator isn't paying attention. So what are some of the things that we can do to help alleviate and remove the cross-threading issue? Within our system, we have a free reverse rotation. And what this does is it allows the tool to spin in the opposite direction of the tightening. So if we are doing a clockwise tightening, we can turn the fastener in the reverse rotation at an adjustable RPM that or a programmable RPM of our choosing, but typically that's going to be a very slow RPM, and we're only going to turn it for about 7/10 of a turn in our example here. And by allowing that allows the first thread to kind of drop into the assembly, and then we can go ahead and reverse or change the direction to the tightening direction and go ahead and do our rundown. We also have the ability to have a soft start setting within the program. So as we go from our reverse direction to our tightening direction, we have that ability to have a very smooth and even transition. So that particular rundown, when that transition happens, it's not real abrupt. Again, allowing that thread to really find itself and run down And then we also have acceleration settings within our controller menu that allow for changes when RPM changes happen. How quickly do we want those changes to happen? And we can increase those acceleration settings to allow, again, for a smooth transition from a slow RPM to a fast RPM within the rundown. And so with that, we can go ahead and take a look at the process. In some cases, you may see operators that are dealing with a fine thread or other type of component where there may be some additional cross-threading or some other errors. They may start that process by hand. And so in this scenario, we're going to kind of replicate that, but we're going to use the power tool to do that, to run down 4 fasteners just to make sure that those fasteners are started and seated. We'll then scan a barcode to confirm that that has happened. Then we'll go ahead and run those fasteners to the final seating torque. We'll also take advantage of the ability to use our free speed and free angle setting within that tool. And as we look at the process, that may be a little bit more clear, but what happens, especially with a long fastener at a lower RPM, the rundown time would take a while to run that down. And for us to be kind of as efficient as possible, we can increase the RPM for a certain amount of turns within that fastener. And again, that's going to allow us to be more efficient, run the fastener down at a faster RPM. Once we get through most of the fastener, the tool will then downshift to its seating RPM and go ahead and run that RPM down for the torque that it is designed for. And that's basically for a lower torque value. We don't want to create any additional inertia by having a fast RPM. It'd be very, very similar to if you're driving in a car. The slower you go, the more accurate you can be when you come to a stop sign on how close you would be to the actual stopping area. So that is kind of the concept behind that. And then we'll also show you how we can set an error proofing angle if we did have a washer stack in there and that washer stack was not present. We would be able to see that within the rundown. I'll show it to you as kind of the reverse of that, but you should be able to get the understanding of what we're looking to achieve by using the angle to help error proof that particular fastener, to make sure that we have the correct amount of washers or other type of stack that may be part of the fastening. So with that, let's go ahead and jump into the demo. And so I have our ECT controller here, and I'll go in and I'll show you what we looked at for those particular settings that we did. For us to be able to get into our settings menu, we have our window up here, and then we'd have to log in to the screen. And now we have the different tabs with different processes that we can do, but mostly what we're going to be looking at here is going to be in our parameter menu. And we have our fastening tab here. And so we're going to be using 2 different presets. We'll use preset 1 to actually set the fastener. Then we'll use preset 2 to do the final torquing for that. So in this case, we do have 2 different types of tightening strategies. So we can do a torque control, you'll see here, which is the TCAM, which is our torque control with angle monitoring. But we can also do the reverse of that, where we're going to use angle to turn the fastener to a certain amount of rotations. But we could also monitor the torque in there as well. And in this case, our target angle is 500 degrees of rotation. So we're just seating, again, the fastener at the very beginning of the rundown just to make sure that everything is seated correctly. And then we can look at our preset number 2. And now we have our torque control with angle monitoring. Our torque value is set at 1.5 Newton meters. We have our RPM speed at 128. We have our minimum angle, so we must meet a minimum threshold turn of 5,500 degrees of rotation. And we have, as I mentioned, our free angle. So for 4,500 degrees of rotation, we're going to run the fastener at 550 degrees, 550 RPMs. And then after that total free angle has been completed, the tool will downshift to 128 RPMs. If we look at the advanced settings that we have for this, in preset number 1, again, we're just seating the fastener. So we're going to use our free reverse rotation. Our speed is going to be very slow, 25 RPMs. So again, this can all be adjusted, and you can basically use whatever settings you want. But for our demonstration purposes, that's where we'll have it. And again, we're going to turn it just 7/10 of a turn for that first thread to drop in, and then the system will go ahead and start with the fastening process. So that's the different settings that we have. Again, we can come in and change those. If we look at the assembly that we have built for this, again, we're going to run or set the first 4 fasteners. Then we're going to need to scan a barcode to confirm that that has been completed. Then we'll go ahead and do the tightening processes. But that's all done within our model function. And so here's where we can create that particular assembly, which is built off of the different presets that we have in the system. And so in this case, let me go ahead and zoom in so you might be able to see this a little bit better. So we have our first is going to be a fastening step. We're going to use preset number 1 for a count of 4. Then we're going to need to scan our barcode that we have here. Next, I'm just going to show you how slow the normal rundown would be at the particular RPM that we have set. I think it's 128, if I recall. Then I will show you the fastening with the auto speed the free speed and free angle. And that will finish our assembly. And we can then start the process over again. Or we can continue and add other processes through this model. You can have up to 20 steps within the model. You can have fastening steps, delay steps, other types of fastenings where you can have input and output communication as well that you may use within that particular setup. So if we come back out to our operation screen, you can see we're using model 1. This is going to be using preset 1, and we're on the first step of that, which is a fastening step. So on our thread block here, I have our 4 fastening locations along with our fasteners. So we'll go ahead and do the demonstration there. And so right now we would be using, again, our preset number 1 just to go ahead and set the fastener. And again, this is going to run really slow in reverse. so the fastener can find the thread. And if I go ahead and run that, we'll go in reverse. And then we went our 500 degrees of rotation, and the system has stopped. So if we continue on, and this could also be done in, as I mentioned, in one actual rundown, but we just wanted to demonstrate how this might work in this type of scenario. Maybe you have a gasket type of rundown that may need to be seated in a particular order, and if there is any type of cross-threading that may happen, that could be an issue. So if you want to set and make sure that all the fasteners are ready to go, and then go ahead and do the tightening, this would be a scenario that you could use. And so now at this time, we've set all the fasteners, and so our next step in the model is to scan our barcode. And so in this case, I don't have any power to the tool, so the tool is inoperable right now until we scan that barcode. And so I have my barcode scanner that's hooked up to the RS-232 port, and once I scan the barcode that we have set, it allows us to index to the next process in the model, which is now we're using preset 13. This is just to demonstrate how slow this would take if we wanted to run this down for the fastening RPM at 128. So that would take a little bit more time than would be necessary. And again, for us to be as efficient as possible, we can use the free speed and free angle. So I'll go ahead and do that now. We've changed to preset number 2. So we're on our 4th step in our model. And so now the tool is going to run at a much faster RPM. Then it downshifts and seats. Okay, and now to just demonstrate the error proofing part of the demonstration. If we did have a washer stack, say of this magnitude for the fasteners that we just did, we could set basically a minimum threshold. In this case, we have our minimum threshold at 5,500 degrees of rotation. And so what would happen during this if we didn't meet that angle? So we have an error that that comes up. In this case, because we're running at a higher RPM before that actually torqued out, we received a torquing error. So we went higher than the seating torque during the free speed and free angle portion of the rundown. However, we still didn't meet the minimum angle requirements as well at the 5,500 degrees of rotation as well. So we received an error with that. And then, so to finish off our model assembly, I'll just go ahead and finish this last fastener. And then we received notification that the model was complete, and now it has reset, and we can do the next batch, or it can move to a different assembly. Within this model, we can then go and do other fastenings within the product, or we could change it to a different model, things of that nature. But that's how we can go ahead and use the smart fastening tool to make sure that for those applications that are really critical, that may require extra attention from the operators, we can go ahead and use some of the settings that we have to be able to demonstrate for you today. So that's going to finish up our presentation. And so now we can move to any questions or answers that we might have. So Chris, do we have any questions?
Hey, Dave. Thanks for the presentation. The first question we have is, what does the bit socket tray do to help prevent errors that you showed early on?
So the bit socket tray allows the use of a specific bit for a specific preset or application. So you may have a scenario where the operator needs to use a certain bit, but they may be able to get away with using a different size bit that's already in the tool. So let's say you've got a Phillips bit, a Phillips 0 and or 00, and then you need to move to do an assembly with a Phillips number 1 or something like that. Something that could work but doesn't work the best and may cause some galling issues or some stripping or threading or errors on the fastener. And so we can put the fasteners within a bit socket tray. So the operator must pull and use the right bit for that particular fastening application. And there are ways that we can ensure that that bit is the correct bit, that they don't just pick one bit out of the tray and put it in another slot, but they actually physically have to go in and change the bit. That is one scenario. Another scenario is that the operator can pull the bit out of a certain location, and that will automatically change the preset or model that the operator would be using. So they can go and pull a bit. It will change on the controller. They can use that bit for the tightenings that they need. They replace that bit, pull another one, and it will automatically change the fastening for whatever bit is being used. So we can kind of use the bit socket tray to either evoke presets, or we can use it as a way of guaranteeing that the operator is using the correct bit for the correct application.
All right, thanks, Dave. The next question was, how can you program the tool to prevent or detect the cross-threading event?
So just as we demonstrated with the use of the washer stack, when we set a minimum turn threshold, if the cross thread is going to happen, it's going to happen right at the very beginning of the fastening. So there's not going to be enough rotation in the fastener for us to count that as a good rundown. So certainly we would hit the torque for sure, but there would only be a slight bit of turn, maybe only 5-10 degrees of rotation with a fastener that, in our case, we had to turn 6,500 degrees of rotation. And so if we set that threshold of a minimum amount of turn, that must happen. So in another scenario, if it takes 3 turns to fully seat a fastener, so that must go 1,100 plus degrees, we can say the fastener must turn at least 900 degrees of rotation. If it doesn't, then we would generate an error, and then the operator would then need to reattempt that fastening. So that's how we would do that. We would set a minimum turn threshold, and it would detect that cross-threading event.
All right, Dave. Next question is, when tightening a fastener into a plastic part, is there a recommended process to follow with this power tool?
So in those scenarios, you may need to look at, if you are having issues, at doing some destructive types of tests to see how the fasteners perform at a certain threshold to yield. point, and then you can kind of back that torque that you see when it fails. You can reduce it to about 75 to 80% of that value. That would give you a good indication of how the fastener would perform in that. If you are doing a tapping, self-tapping type of fastening, we do have the ability to monitor what happens during that rundown. So you can either, if it's a scenario where you need to cut the thread, and then the torque may be higher during the cutting portion than the actual seating of the fastener. We do have some modes and settings that allow you to compensate for thread cutting. If you, in that scenario, that would be for the plastic type of setting. But again, we can also then monitor the RPM. Do we need to slow that down so it cuts with more uniformity than it would be if the RPM was really fast? Is there a scenario where we may need to use the free speed and free angle to kind of start that process to cut the self-tapping process and then slow it down as it gets close to the seating portion of the fastener? So there are other ways that we can look at trying to precisely set those particular fasteners that are thread cutting into plastic.
All right. Thanks, Dave. The next question is, how do you know what threshold to set for an angle rotation for a specific fastener? Is there a way to learn that value?
Yeah, so we do have an automatic mode where you can run the fastener down. The system will learn the characteristics of that fastener, and it can pre-program it for you. Or you can do it on the display. It shows the total amount of turn or angle for the fastening rundown. So you can do several examples and get that information straight from the controller operation screen. And then you can go in and make those adjustments to the free speed and free rotation.
All right. Thanks, Dave. And that looks like that's the last of the questions we got.
All right. Well, I thank you very much for sticking with us today. It went just slightly a little bit longer than we normally do, but nevertheless, thanks very much for joining us today, and we look forward to seeing you in the next one. So happy holidays, and we'll see you next year.